The fourth and final type of resolution we're going to talk about is radiometric resolution. And this is probably the one that's least talked about and often most ignored in discussions on remote sensing. But it's quite important. I hope to explain why. So first of all, the definition. We can think of radiometric resolution as the sensitivity of the measurements that are taken. Now, what does that mean? Now imagine the sensor is a ruler to measure light. The better your ruler, the better you can measure. So for example, the images that are being collected are in different bits. These are computer files which have different levels. So for example, a 2-bit file has 4 different levels in it, which is basically 2 squared, 2 to the second power equals 4. A 3-bit file has 8 different levels, that's 2 to the third power equals 8, and so on, such that an 8-bit file has a total number of 2 to the 8th power of 256 different levels. So imagine that these lines here, these vertical lines, are rulers, and these little marks, which represent the number of levels, can be thought of little gradations on the ruler. Now let's say you want to measure some things, in this case happy faces. What are the sizes of these happy faces if we're using a 2-bit ruler? Well, this is 1, 1, 1. This guy might be 2, and this one's 3. These ones are so small you can't even really measure them, so you get a value of 0. If you upgrade from a 2-bit ruler to an 8-bit ruler that has 256 marks on it, then you have a completely different picture about what relative sizes of these objects are. So for example, 47, 63, 79, you get the idea that we have a much finer look at the sizes of the objects we're trying to measure when we use a finer ruler. Of particular importance are these values that originally came as 0 in the original measurement with the 2-bit ruler. Often in remote sensing we'll have dark areas like water or shadow, and if we have a 2-bit ruler or a very low resolution radiometric resolution sensor, you might not really be able to measure those. However, if you have a higher resolution sensor, radiometric resolution sensor, then you can actually get values. And the better the resolution, the finer the values you can get. And that's this little area down here when we're looking at, let's say, water, shadows, or dark things. The difference is pretty remarkable. Now, for the sensors we've been talking about so far and a few others, what is the radiometric resolution? The original Landsat thematic mapper that flew on Landsat 5 it's out of commission now, had an 8-bit radiometric resolution that allowed 256 different levels. So if you're thinking about the shadows, there were 25 different shadow levels. That's not bad, and there's a lot you can do with it, but newer sensors have higher radiometric resolution. So for example, Worldview 3, this is a very high resolution, spatial resolution sensor, which is flown by Digital Globe. It's got 11 bits, so that means 2,048 different levels. The Enhanced Thematic Mapper and the Operational Land Imager on Landsat 7 and 8 respectively have 12 bits, as do MODIS and Sentinel. All of those are able to produce over 4,000 different levels. So that means you can measure 4,000 different values with the ruler that they provide you. And the shadows, you get a lot of different values too. Pulsar, I've put not applicable because traditionally radar imagery is reported in decibels, and the scale and the concept of radiometric resolution just doesn't really apply, and we're going to talk a lot more about that later. But what we can do is think about how good is the Pulsar ruler at finding different objects in a scene. So if we look at the histogram for one of the Pulsar bands that we'll be working with here, the values range from, well, let's say around 1,000 up to, well, 10,000 and more. And actually the scene I'm going to show you, values go up to, I think, 40,000 or so. So values go from, a range of perhaps 40,000 different values. All right. If we actually look at the image itself, I've pulled up this tool which you can get some values for each pixel that I'm hovering over. You can see that value changing right over there. If we look at a dark part, this is a reservoir right here. As we know in radar, the water is usually dark. So the values here are going, well, there's a 726 is the value for this one. Yeah, basically in between 1 and 2,000 are the values. If we zoom out a little bit and go to some of these brighter paddy fields, this is rice that's growing well and has a lot of backscatter. Let's see in here, yeah, 19,000, 16,000, 23,000. So overall, the values that are in this scene are quite diverse and give an indication that something like radiometric resolution of the pulsar image is quite high. In fact, if you calculate the range of values here between, let's say, approximately 0 to 40,000, that is equivalent to approximately a 16-bit sensor. Right? So that would be 65,536 different total levels and a lot of values in the shadows. Now, I put a question mark here, an approximate sign, because that's not an exact comparison. But the main point is that with Pulsar 2, you've got a tremendous range of values for the images radiometrically that you're getting back.